So subsection are something like EM wave, energy transport and Poynting vector, radiation pressure, polarization, reflection and refraction, total internal reflection, and polarization by reflection. So at the very beginning, so we have the Genesis, which is the first book of the Bible, first book of the Bible. 创世纪的第一章第1到3节。So this is the NIV version. NIV version. So in Cantonese, it's something like 起初神創造天地，地是空虛混沌，淵面黑暗，神的靈運行在水面上。神說要有光，就有了光。So according to Bible, at the very beginning, as you may know, God spent 6 days to create the world and have a 1-day rest. So we have Sunday. You may ask why God doesn't create the world in 2 days and rest for 5 days, so that we may have 5-day rest every week. But that's the case. And at the very beginning, it's mentioned that at the first day, God really created light. Let there be light. 神说要有光，就有了光。But before He created light, there were already some waters. And you may ask, what is the world is before God created the world? And according to the Big Bang theory, there's no time before the Big Bang. The time does not exist before the world is created, the universe is created, or the Big Bang start. And actually, at that time, there is no space at that time, and you know that the universe is finite. There's some sort of with the boundary, but it's hard to describe. So actually, Maxwell finds that this is the Maxwell rainbow. So in this segment, it is the visible light from red to violet, and actually to the right hand side, the frequency is higher, and to the left hand side, the frequency is lower, and the wavelength is longer. So which means that within the visible light, the red light has the longest wavelength, and for the violet, the wavelength is shorter. And actually, out of the visible light, there are many electromagnetic waves. Compared with other light, electromagnetic wave, the light has a quite high frequency. Radio wave is somewhere here. It's around 10 megahertz, tens of megahertz to gigahertz. So, for example, if you use Wi-Fi is around 2.4 gigahertz, 5 gigahertz. For GSM, WCDMA, LTE, you actually use the frequency around 800 megahertz to up to 2 point something gigahertz, not more than 3 gigahertz. And if you have listened to the FM radio, they're using 100 megahertz, which means the wavelength is even longer. And recently, you know that there are 5G. 5G use the millimeter wave, which is around 60 gigahertz or 28, 29 gigahertz. So the wavelength is around millimeter scale. And as you know, for the Wi-Fi, the wavelength would be 10 times longer. So it's around centimeter level. And this is the long wave with low frequency. So higher than the visible light, we have ultraviolet. And this is the infrared, the 红外线, 紫外线. So this part is the X-ray. So it's a high energy particle and with short wavelength. So it can go through some of the meat or skin, so that you can check the bone or whether there are some lung disease. And for even higher, it is something like the gamma rays. So which is a very high energy particle. So in Maxwell time, the visible ultraviolet form of light were only electromagnetic wave known at the time. According to the Maxwell equation, they can predict the existence of the electromagnetic wave. However, Hertz discovered what we know the radio wave and verify that they move through the library at the same speed as visible light. So actually, the EM wave move at the speed of light in the air. Indicate that they have the same basic nature as visible light. So now bright spectrum of EM. So it's known as the Maxwell rainbow. So here it tells you that how do we create or generate the EM wave. So suppose we have an energy source. We provide some sort of energy to storing some energy in the capacitor. It is LC resonator. So it will oscillate at 1/2 pi square root of LC. So suppose you have an adequate capacitor and inductance, then you can generate the electromagnetic wave with the desired frequency, and this one pass through the transformer and goes to here. This is something like the electrodipole antenna. So it is a sort of antenna, and in this case, we can generate the electromagnetic wave. And if you choose a point which is quite far away from this, then you will observe that there's a wave traveling past it. And that's why I need to tell you the differential form of the Maxwell equation, because you can try to manipulate the current here, so that according to the Maxwell equation, you can solve the electromagnetic wave generated by this antenna. And of course, you can use an antenna far away and then to receive this signal. This is what it mentions. P is a distant point at which a detector can monitor the wave traveling passive. So we can use the electromagnetic wave to transmit some information. So there are some observation, something like this. When we generate the EM wave, the electric field E and the magnetic field change with time as one wavelength of wave speeds sweep past the distance of p. So you can see both electric field and magnetic field actually on the whole space. But if you put the detector here, you detect the electric field and magnetic field at this point. The wave is traveling directly out of the page. We choose a distant point so that the curvature of the wave is small enough to leave length, which means that P is very far away. And as you see here, it's something like a circle. But if the radius tends to infinity, we feel like it is actually a plane wave. So you see something like this. If this is very far away, and then you cut this part, then you'll see, oh, this is a very, very large circle. But if you just cut a segment of it, then you feel like, oh, it is a straight line. So such point, the wave is said to be a plane wave. So we will feel that the wave is a plane wave, something like this, to propagate. And you feel that the electric field is large here, pointing to the bottom, and try to decrease. Also the B field try to decrease, and this point is 0, and then later pointing to the other direction, and then become the largest, pointing to the opposite direction. This is left, this is right, this is down, this is up, and through looping forever. So there are some key features that are present regardless of how the wave is created. To be honest, you feel that it will be hard to understood because it tries to tells you the truth, but you may not know why, because this is hard to explain it clearly without the math. So in the next lecture, I will also tell you how to solve the wave equation so that to get this result. But today you try to know what it is and leave why at next week. So there's several observations. The first one, the E field and B field are always perpendicular, which means that E field is up down and the B field is left right, or maybe because we have 3 dimensions, but they only occupy 2 directions. Second one is E field is always perpendicular to the magnetic field. The first one is E field, B field are always perpendicular to the direction in which the wave is traveling. The second one is that E field and B field are always perpendicular. So that the second one means that E field up down, B field left right. And the first one mentioned that if the E field oscillating up down, B field oscillating left right, then it is propagating out of the page, which means the EM wave, suppose the EM wave is going this way, and then the E field should pointing upward, and the B field should point into the page. So it should be something like this. This is the E field, and the direction of propagation. And then the third one, the cross product, E cross B, always give the direction in which the wave travel. So you see E cross B pointing outside, E cross B pointing outside, E cross B pointing outside, pointing outside. So as long as they pointing outside, E cross B is the direction which the wave travel, and later you know that actually E cross B is proportional to the vector called pointing vector. The field always varies sinusoidally. Moreover, the field varies with the same frequency and in phase with each other. So for the plane wave, it is a sinusoidal wave. But actually, for example, if we use to transmit data, then it will never be a sinusoidal, because sinusoidal cannot carry any information. But if it is not sinusoidal, how would it be? You use the Fourier transform to separate them. Then you have many different sinusoidal waves, and then they can add together. Because Maxwell equation is linear, so that you can have many different sine waves with different frequency, and then they can combine together to form a different kind of waveform. So here we know that with this observation, we try to write out the E field is a sine wave, EM is the amplitude of the E field, BM is the magnitude of B field, and actually they multiply by sine kx minus omega t, sine kx minus omega t. But E point to, for example, x direction, B point to the y direction, and then the EM wave propagate in the z direction, something like that, because x cross y will be z. EM and BM are the amplitudes of E and B vector. The E field induce the magnetic field and vice versa according to the Maxwell equation, or more specifically, due to the Ampere's law and the Faraday's law. And K is called the wave number. It can be written like this: 2 pi over lambda, which is K. So if I have time, I'll teach something like the quantum mechanics. And in signal and system, you know that you do the Fourier transform from time domain to frequency domain. But actually, in quantum mechanics, they do the Fourier transform from x domain to k domain. And this is related to the Heisenberg uncertainty principle. Actually, it is something like a Fourier transform. Then, at that time, Heisenberg tried to prove that for a Gaussian distribution, the Fourier transform of them multiply to be a constant, and which leads to the Heisenberg uncertainty principle. So here, k is the wave number, which is inverse proportional to the wavelength. And omega is the angular frequency, 2 pi f. And maybe there is another identity you need to pay attention is C equals F lambda. I suppose you should have learned it in high school, but this is really important. This identity is really important. C equals F lambda, or V equals F lambda. But here, as we know, it is electromagnetic wave, so the speed of the electromagnetic wave is always speed of light. So C is F lambda. So as long as we have a higher frequency, the wavelength is smaller, and vice versa. And C is always constant in free space or in the air. It is always 2.998 times 10 to 8 meter per second, no matter what is the speed of your inertia reference frame. And I will tell you in chapter 37, the relativity. So, so actually, as long as F and lambda are inversely proportional, so K and lambda is also inversely proportional, which means that K and F should be proportional. And omega equals 2 pi f. I think you should know that. So f is the frequency and omega is the angular frequency. Lambda is the wavelength. Okay. So up till now, any questions? Size. Okay. Actually, so if you, for example, if we fix x to be 0, then these two equations will become em psi minus omega t or em psi minus omega t, and then we can put the minus sign outside. So it's something like another e minus em, maybe you can call it em prime, minus bm, you can call it bm prime. So that it is a amplitude multiplied sine omega t, which means that at here, for example, at time t equals to 0, then it has the maximum amplitude, and then for sine wave, it tries to it will decrease, because you know a sine wave is something like this sine wave. So you can imagine at the first 0 point it is here, and then at that point it try to go up, and at that point go to the peak and going backward, going to the 0 and going down, going in third quadrant and going back to the 0 point, something like that. Maybe I can show you a graph. Actually, something like this. So the EM wave is propagating this way, and the E field is going up down, and the B field is going left right. It should be something like that. And you see that, oh, it seems that the wave is propagating, but actually it's not. Actually, it's not. Actually, if you just look at a point, it's go up and down in a side wave, but actually in the space, it's also going that way. It's pretty hard to explain. I'm not sure, but I'm not sure if you go to the wind, there's the cable car. Do you know? 那个永利啊，永利那边不是有那个缆车吗？那边不是能看到一个喷水的 ？You can see the fountain. Actually, the water doesn't move, but the water only going up, down, up, down. But actually, you feel that the wave is propagating. Actually, for each point, for example, if I just, oops, I cannot stop. For example, if you just look at a point, actually the red bar is only going up, down, up, down, up, down. But actually, according to the Maxwell equation, this changing will lead to generating induced E field and B field. So it will generate the B field at the neighborhood, and then it will look like something okay. It's just like taking the differential, taking the derivative, because in the Faraday's law, the changing B field will lead to changing E field. So actually, it is changing, so it will induce the field, and then it will look like it is really propagating. And in the next lecture, I'll try to solve the wave equation. Maybe you'll get more insight about that, because it is very hard to explain why it will look like this. Yeah, if I just throw away all the math, it's something like this, then to be honest, it's really hard to understand. So we will try to derive the wave equation from the Maxwell equation in free space. In free space means as you know, the differential form of the Maxwell equation is something like this, and the free space means rho and j is equal to 0. So this is 0, and this is 0. Then the Maxwell equation will reduce to this, and we'll go through it next week. And actually, we can derive the wave equation here, and we try to solve this PDE. Then finally, this is the solution of that. So you may ask why it will look like this, because we need to solve the PDE. The answer is this. So let's come back. Okay. So, any other questions? In my opinion, you don't really need to pay too much attention to. But it's just a demonstration. It tries to tell you that actually this is the fact. It tried to use a figure to to visualize it, but I'm not. I don't think it's a really good presentation of it. But if I just remove it, then it will be even harder because there are lots of text and some equation. But actually, it tells you that okay, the E field is actually varying in a sine wave form. So it is something like if you fix the time, you will see it's a sine wave. If you fix the x-axis, it's also a sine wave. So in both cases, they are sine wave. Which means that at the figure just now, this is fixed time, so you will see a sine wave. But if you just look at one bar, and maybe you draw it with versus the time, you will also see it is varying in a sine wave. The reason why is that it tries to maintain the phase. Because you have this one. Which means that if t increase a bit, the x should decrease a bit. No. Which means that if this one is a constant, then if t increase a bit, x should also increase a bit. So then this is a constant. And actually, we know that the speed of the wave is omega over k, which is I just mentioned c equals f lambda. C equals f lambda. C equals f lambda, and f omega is 2 pi f, and k equals 2 pi over lambda. So if you just substitute f equals omega over 2 pi and lambda equals 2 pi over lambda, 2 pi over k equals 2 pi over lambda, k equals 2 pi over lambda, then you get the speed is actually omega over k. And the speed of light is 1 over square root of mu 0 epsilon 0, and it is more precisely 2.998 times 10 to 8, more precisely, or 2.997 92458, something like that. And in the chapter 37, in the relativity, you need to use this because it is important to make the speed of light accurate enough. Otherwise, the error will be quite large. And here it mentioned that all EM waves, including the visible light, have the same speed, c in vacuum. Also, okay, you should ignore this one. I just forgot to delete it. And actually, the amplitude ratio between the EM and the BM is also C. So next lecture, I will show you why. So based on this, we will also define the Poynting vector. Poynting vector means the rate per unit area which the energy is transported, which means the EM wave has some sort of energy, and this Poynting vector has the direction equals B, which is the direction of the EM wave, and actually the magnitude of it is the energy per unit area. And also we can define the intensity of the EM wave, which is E, the root mean square. The square of the root mean square electric field over the C mu 0. And as you know, RMS is EM, the amplitude over 2 square root of 2. You can simply derive it using the integral EM sine omega t square dt from 0 to t and over 2t, and take the square root. Should be something like that. Then you can derive this really EM over square root of 2. And actually, and this is the intensity of the EM wave. Just it's something like you go outside and then you see the sun. How strong it is the intensity of the EM wave or the light. And of course, light is a sort of a EM wave. And actually, the intensity is something like the power, if it is generated by a point and it is propagate with a spherical surface. So the whole power transmitted from here is normalized by the surface area 4 pi r squared. So we have a sample problem. So when you look at the North Star, you intercept light from a star at a distance 431 light year, emitting energy at rate 2.2 times 10 to 3 times that our sun, neglecting any atmosphere absorption find the RMS value of the EB field when the starlight reaches you. So okay. So okay, so R is 431 light year. Light year means you multiply it by 3 times 10 to 8, or more precisely 2.998 times 10 to 8, 8 to 10, 10 to 8, 10 to 8. Times a year has 3,600 seconds times 24 times 365.25. Yeah, because every year we have 365.25 days. So it will become 4.08 times 10 to 18 meter. 18 meter. And we know that I equals PS over 4 pi r squared, which is also equals to ERMS square mu 0c. So ERMS would be PS mu 0c over 4 pi r squared. Take the square root, which means we just multiply. We multiply this part to here and take the square root. So it will become 3.9 times 10 to 26 times 2.2 times 10 to 3 times 4 pi times 10 to minus 7, also times 3 times 10 to 8 over 4 pi. R is 4.08 times 10 to 18 square. The square root. So E, it will be 1.24 times 10 to minus 3 V over M or N over C, depends what you like. So this is the ERMS, and I think I need another page for it. And for BRMS, which is actually ERMS over C. So it is 1.24 times 10 to minus 3 over 3 times 10 to 8. So it is 4.1 times 10 to minus 12 Tesla.